There exists a cosmic body in the universe unlike anything else. It has no form, no light, no surface to touch, yet it can bend space-time itself, and its pull is so powerful that not even light can escape. Born from the death of massive stars, it compresses matter into an infinitely dense point called singularity, where the known laws of physics collapse, and around it lies a boundary called the event horizon. Once you cross it, there is no return. Although we don't understand it fully, we know it's there, twisting light, bending time, and anchoring galaxies. And this cosmic body is what we call a black hole. And it was Einstein's own theory of general relativity that reshaped our view of the universe, where his equations showed that when a massive star collapsed into infinite density, gravity could grow without limit, creating a region where not even light can escape. Yet, Einstein himself dismissed this idea because to him, the idea of a star collapsing into infinite density, leaving behind a hole in the universe where not even light could escape, sounds too bizarre to be real. And he thought nature would not allow such extremes to exist. So his equations might have revealed the truth, but his current understanding of physics refused to accept. And over the decades, the observations became impossible to ignore. Astronomers found stars collapsing into darkness, light bending around invisible mass. So, piece by piece, evidence was stacking fast, and slowly people were realizing these cosmic bodies were not just mathematical equations. They were real, massive, and invisible objects hidden across the universe. Now, before we understand what black hole is, we have to go back around 2 centuries ago, where the idea of dark stars actually started. See, long before Einstein, in around 1783, a natural philosopher born in 1724 named John Michell proposed the existence of dark stars, where he said if a star is massive enough, then its gravity will be so strong that it would be impossible to escape. Even full light, which we consider to be the fastest thing in the universe. And around the same time, the French mathematician Pierre Simon Laplace explored similar ideas, who described these invisible stars mathematically. But the world barely noticed, because in an age dominated by telescopes, people were more interested on seeing visible stars than those hidden in darkness. Now, fast forward to 1915, Albert Einstein, the one obsessed with gravity, gave his theory of general relativity, which revealed that gravity wasn't just a force that pulls objects together. It was actually the curvature of a space-time itself, where massive objects bends the very fabric of reality. And within his equations was a possibility of a place where gravity is infinite and space-time gets folded upon itself, a place where not even light can escape. And even though his equations showed him the reality, but as we already know, he refused to accept the truth and thought the universe would not allow such extremes to exist. But in the middle of World War I, a German physicist named Karl Schwarzschild started working silently, driven by curiosity and brilliance. He started solving Einstein's equations, and he was able to solve the first exact solution, creating a mathematical blueprint of an entire black hole. His equations revealed the possibility of a star collapsing into a point of infinite density, named singularity, and surrounding it is a boundary we now call event horizon, which once you cross it, there is no return. And even though he did not name it black hole, but he definitely created a skeleton of how black hole might look like. So now that you know how black hole was discovered, let's start understanding the actual structure of a black hole. So at the very center of a black hole is a point named singularity, where density becomes infinite, where mass of stars or billions of suns is compressed together into a space smaller than an atom, with escape velocity way more than the speed of light. Here, gravity is so extreme that nothing we know can escape, not even light, which we consider to be the fastest thing in the universe. By the way, escape velocity is the minimum speed required to escape a planet's gravitational pull out into space without falling. Anyway, here space-time is bent to infinity, which is why event horizon forms, where time slows down dramatically. Also, this is one of those mysterious places in the universe where our current knowledge completely fails, where we can't really explain what actually happens to the quantum information that falls in. Now, moving on to the second part is the event horizon. See, this is not a literal surface, it's just a mathematical boundary that we humans have defined. And crossing the event horizon means you can't send information back out. Because once you cross it, everything will keep falling towards the center of a black hole, with infinite gravity pulling you inward. Where even if you travel with the speed of light to come out, you still can't do it because compared to infinite gravity pulling you inward, your speed of light would be negligible. So you will only fall inward towards singularity. Now, before we understand the next part, we need to understand what Schwarzschild radius actually is. So, Schwarzschild radius is nothing else but the radius of the same event horizon that we just discussed. And its mathematical formula is Rs is equal to 2gm divided by c square. And this is one of the main ways we determine the boundary of event horizon. So now comes photosphere, the third main part of a black hole. And just outside the event horizon lies this photosphere. Here gravity bends light so strongly that light particles can orbit around the black hole in a perfect circular path. And it is special because light is usually considered to travel in a straight line. But here gravity is so strong that it bends the space-time itself, leading to photons orbiting around the black hole in a circular path. But this orbit is unstable, due to which if a photon is pushed slightly inward, it falls directly into the black hole. And if it's pushed slightly outward, it escapes outside, farther away from the black hole. Now, the fourth main part is accretion disk, which is one of the most unique sights you can see in space, where as gas, dust, and even whole stars falls towards the black hole, they don't dive straight in. Instead, they spiral and forms a glowing disk that spins at nearly the speed of light. And inside this disk, friction and the immense gravity heat the matter to millions of degrees, causing it to radiate X-rays and gamma rays, which often lights it up, making it glow more than anything else in the entire galaxy. But what makes it more astonishing is the bending of space itself, where light from the disk does not travel in a straight line and bent by the black hole's gravity, which means we can also see the parts of disk that lies behind the black hole, where light from the far side comes around the black hole and reaches our eyes. And the result, it forms a glowing halo-like structure, making it one of the most beautiful scenes you can see in space. Now, in the accretion disk, as these gas and dust particles gets heated up to around millions of degrees, it slowly drifts inward and falls towards the event horizon, where eventually some particles falls straight into singularity, getting lost forever. But for a lot of particles, as it spins, the friction and turbulence makes it so hot that atoms are ripped apart into electrons and nuclei, leading to what we call plasma. And this plasma is highly ionized, so it drives magnetic field lines with it, where these fields uses black hole's rotational energy or the energy of accretion disk, where plasma gets accelerated to nearly the speed of light, blasting away like jets perpendicular to the disk, straight out of the black hole. And this is what we call relativistic jets. And now is the perfect time to learn about a term named Hawking radiation. So this blasting of jets and matter falling in from the event horizon is the main key part of what Stephen Hawking explained, where he said, even though we assume nothing can escape the event horizon, but quantum mechanics predicts that particle and antiparticle constantly moves in and out of the existence near the event horizon, where on one hand, while one particle falls into the black hole, the other escapes to infinity. And to observer outside the black hole, the escaping particles looks like radiation coming out of the black hole itself. and this process causes the black hole to lose mass over time. Because the particle that falls in has negative energy relative to infinity, so the larger the black hole is, the colder and weaker the radiation will be, and the smaller the black hole is, the hotter and faster it evaporates. And this is what we call Hawking radiation, which basically says that black hole is not some eternal body that will last forever, because it will also eventually die and evaporate. It's just that it will happen super slowly over time. Anyway, moving on, we now have the last main part of the black hole called Doppler beaming. So, this Doppler beaming is a unique effect that we see in a black hole, where when material on one side of disk comes towards us, the light waves which it emits gets compressed, making it appear brighter and slightly blurry, while the opposite side moving away from us where light waves get stretched makes that side dimmer and more reddish. And this is not because black hole itself is tilted, but it's actually just an illusion created by relativity of how light bends around the black hole. So now you know what black hole actually is. But here are some mysteries that our current understanding of science either can't fully explain or can't find its existence. Out of which the first one is white holes. So, as the name suggests, white holes are considered to be a theoretical opposite of black holes, where unlike black holes that absorbs everything in, white holes on the other hand expels everything out, where nothing can enter and everything is just thrown out. And mathematically, white holes are allowed solutions to Einstein's equation, but unlike black holes, we have never found one in nature. And here is a question that comes in mind when talking about white holes, which is that if white holes are throwing everything out, then it has to have something inside of it which is absorbing everything in to be thrown out in the opposite end. So, if it is a possibility, then there has to be something connecting both of them too. And here is when the concept of wormholes comes in, where in 1935, Einstein and Nathan Rosen proposed that black holes might be connected to white holes, the theoretical opposite of black hole, and forming a bridge between them through space-time could be something called wormholes. And in theory, such tunnels could link distant regions of the universe, or even parallel universes, but in reality, wormholes are unstable. The slightest disturbance, even a single photon, could cause them to collapse instantly, unless exotic matter with negative energy exists to hold them open. But the question is, do such materials exist? And the answer is, we don't know. For now, wormholes is just a possibility because we don't have enough tech to find one yet. And these cosmic objects like black holes push our knowledge to its limit, which helps us understand we still need to learn a lot about the universe. And these terms like white holes, wormholes, or possibility of another universe is not just science fiction. These are some of the serious questions asked by the smartest minds of our time. And it is also proof that everything starts with curiosity, to think beyond our understanding, to discover something our current knowledge can't really explain. And black holes are the perfect example of that, where from the possibility of dark stars to Einstein proving it mathematically, to him not accepting his own equations that showed him the truth, to the actual discovery of a black hole. It is a remarkable example of curiosity turning into reality. And still, there are a lot of things that we have not yet discussed, like what are different types of black holes that are found or expected to be found in nature, or what would happen if you fell inside a black hole. Will you turn into a noodle, or will you get transferred into another dimension? And these topics deserve a whole different video, and that's what we will cover in the next one. Anyway, now you know what black hole actually is. If you enjoyed this video, then make sure to give it a like, and for more such videos, don't forget to subscribe the channel. And I'll see you back in the next one. Till then, tata, bye bye.